Hi, my name is Jeremy Sands, and I'm going to be presenting the paper Multi-Level Anomaly Detection in Industrial Control Systems via Package Signatures and LSTM Networks. So I want to start by acknowledging the authors, Cheng Feng, Ting Li, Deep Chana, and they're from the Institute for Security Science and Technology at the Imperial College London. And this paper was originally presented at the 47th IEEE/IFIP International Conference on Dependable Systems and Networks that was held in Denver, Colorado, June 26th through 29th, 2017. And if you're interested in reading this paper, the link is at the bottom of the slide. So, industrial control systems, or ICSs, used to be very air-gapped, meaning they weren't connected to any outside networks. But increasingly, they're becoming more interconnected. This is to allow for remote control, to improve efficiency, and to allow for supervisory control and data acquisition. So those are SCADA systems. And because of this, ICSs are increasingly at risk to cyber threats. This is important because ICSs are widely used in critical infrastructure. So in power plants and power transmission, water treatment plants, gas pipelines, manufacturing, these all typically involve some form of ICS, and they are also prime targets for malicious hacker groups or nation states. And this is a problem because conventional intrusion detection systems that you might use on a traditional IT network are not suitable for protecting ICSs. So some of the reasons why traditional intrusion detection systems don't work with ICSs is because ICSs typically use specific communication protocols such as DMP3 or Modbus, and a lot of intrusion detection systems don't consider these protocols. And there's also a lack of real-world data sets from industrial control systems, which could be used to train and evaluate different intrusion detection systems. And then also industrial control systems are often involved in controlling physical processes, which can have a lot of noise and complexities that can make intrusion detection difficult and can lead to a lot of false positives. But there are a number of things that make industrial control systems easier to monitor for intrusions. So they typically have very static topologies, and the traffic on these networks is usually pretty regular. And the protocol used are typically pretty simple. So looking at some previous work at intrusion detection systems for ICSs, a lot of them will involve blacklists, which will be a list of known exploits, and they'll check packages to make sure that they aren't one of these known exploits. And the problem with this is that it can't protect against unknown or zero-day attacks. It just relies on whatever attack being part of this known blacklist. And there are also some models that try and learn the normal behavior of these ICS networks and use that model to determine whether or not a package is an anomaly or not, whether it fits into that model of normal behavior. And increasingly, there have been some efforts to use machine learning methods to do intrusion detection for ICSs. And um, what separates the paper in question from these methods is that a lot of these don't consider temporal relationships between packages. So they only consider packages one at a time and try and classify them as anomalous or not. So looking at this framework, it's a two-stage anomaly detection framework. So there's a package level, which is considering packages individually and trying to determine whether or not an individual package is an anomaly. And then after that, there's a time series level, which considers a series of packages and looks at the temporal relationship between packages to determine whether or not a package in question is an anomaly or not. And both of these levels are trained using a data set of non-anomalous network traffic data from an ICS. And at the end of the paper, they evaluate their framework using a real-world data set, which was collected from a gas pipeline testbed that was injected with randomly timed attacks. So looking at the package level of this anomaly detection framework, it starts by collecting a data set of normal network data. And once that network data is acquired, then it's signatures are generated for each of the packages, and we'll touch a little bit more on what signatures are after this, but it's essentially a unique identifier for a package and a database of all those packages from the normal network traffic data set is built. And then when a new package comes in, it's checked whether or not that package is part of the database. And if it's not, it's considered to be an anomaly. So looking more at the signatures, the signature is just a unique identifier of a package that's built using features of the package itself. So this is from the gas testbed dataset that I mentioned earlier. So these are some of the features that are part of the package payloads sent to the SCADA system. And what happens to generate a signature is that these features are concatenated into a string with some special character separating them. But the problem with this approach is that a lot of these features are actually continuous. And in order to build a signature out of them, we need to first discretize these features. So there are a few different methods for doing this discretization. So one method would just be to divide the domain of a feature into equal size bins. And this can either be the known domain if you know a feature is going to be between 0 and 100, just based on what it physically represents, if that's a pressure sensor or some other thing with a known domain. Otherwise, you can use the domain observed in the training data. So divide the min and max, the range between the min and max value observed in the training data, and split that into equal size bins. So that's one way of discretizing a feature. Another one is to look at the distribution of that feature throughout the training data set and look for any natural clusters. So for certain features, there might be very visually apparent clusters that can be used as an easy way of discretizing that feature. And in cases where there's not natural clusters present, then you can use an unsupervised k-means clustering, which is an unsupervised algorithm for clustering data. And an interesting thing with this is that you can actually combine multiple features together into a single part of the signature. So if those features are highly correlated to each other, then you can cluster them together into a single part of that package signature. And there are a few problems that make this discretization difficult, or more complicated at least. And so one is that the granularity with which you discretize can have a big effect on the performance of the anomaly detection. So if you discretize too finely, then similar packages are going to end up mapping to different signatures, and you're going to end up with a lot of false positives. And conversely, if you discretize too coarsely, then very dissimilar packages will end up mapping to the same signature, and you're going to end up with a lot of false negatives or anomalous packages that don't get picked up by the intrusion detection system. So the solution this paper uses is to split the training data into a training set and a test set, or a training set and a validation set. And then the validation set is used to test multiple granularities, and then you can choose the finest granularity that achieves an acceptable false positive rate. And in terms of what that granularity means, that would be if you're doing an even interval partition, that's the number of intervals, or if you're doing some sort of clustering, it would be the number of clusters. And so another issue that complicates the discretization process is that discretizing can make obvious anomalies appear normal. So if this was two clusters from your training data, this would be two features. You see there's two very clear clusters here. Now let's say you have a new package that has this set of features. This package is going to be mapped to the closest cluster. And so in this case, that's cluster 2. And you're going to lose any information telling you that this data point is actually pretty far from that cluster. So the solution they use is to add an extra class. So if you were originally going to have two clusters, you'll add a third cluster that'll just be used for any data points that don't fit nicely into the two clusters from the training data. And you can quantify this by saying, any point that is a greater distance from the centroid of the nearest cluster than any of the points in that cluster, then that data point could be considered part of the extra class that you add. Or if you're doing an even interval discretization, then you can say if there's a data point that's a certain distance outside of the domain observed in the training data, then you can say that that point is part of the extra class. Um, and so once we have signatures generated, then we want to generate a database of all those signatures. And so this is going to be a collection of the signatures for all the non-anomalous packages from that training data. And in order to store these, we need a data structure that's both memory efficient and then also supports uh, quick memory checks. So if we have a lot of signatures in our database and they're just stored in a list, then we're going to have to iterate through that list every single time we want to check whether or not package signature is part of that signature database. And that's going to take a long time, and it's not really going to be an efficient way of doing intrusion detection. So they solved this problem using a Bloom filter. And a Bloom filter is a probabilistic data structure that's similar to a hash table, except each key maps to a single bit in a bit array as opposed to mapping to some value. So if this is your bit array, and in this case it's size M, then you take a package that's coming in, and to check whether it's anomalous, you discretize it, and then you generate a signature for it. And that signature passes through a hash function, and the output of that hash function is modded by the size of the bit array. And that gives you an index into the bit array, and you can check, and if the value stored at that index is 1, then the package is part of the signature database. And if it maps to a 0, then that signature is not part of the signature database and would be considered an anomaly. And in order to prevent collisions, you actually end up using multiple hash functions and then checking if the output of every one of them maps to an index that contains a 1. And in that case, then you consider it good. And if any of them don't map to a 1, then that signature is considered an anomaly or not part of the signature database. Um, so looking more at the Bloom filter, as I mentioned, you can still have false positive lookups. So signatures that aren't part of the database that the Bloom filter says are part of the database. And this can happen if a signature just happens to map to indices that all contain ones. And the frequency that you have these false positive lookups is affected by the size of the bit array, as well as the number of hash functions used. And there's a trade-off that if you have a larger bit array and more hash functions, you'll have less false positives, but you're also going to be less memory and time efficient. And the nice thing about the Bloom filter is that false negative lookups are not possible. So if you go and hash a signature, mod it by M, and each of the indices it maps to contains a 1, or if any of them don't contain a 1, then you know for certain that that signature was not part of the signature database. So just considering the package level of this intrusion detection framework, let's consider some sources of error. So in terms of false positives, which would be normal packages that are flagged as malicious, this could be caused by having too fine of a discretization granularity, and it could also be caused by having too limited of a training data set. So if there's some traffic that's part of normal operations that isn't captured during that training data collection period, then afterwards that traffic is going to end up being flagged as anomalous by the intrusion detection system. And in terms of what could cause a false negative, which would be a malicious package that isn't caught by the intrusion detection system, this could be caused by having too coarse of a discretization granularity. So a malicious package, when you're generating the signature, it ends up getting discretized to the same signature as a package that was part of that training data. It could also be caused by a Bloom filter collision. So that would be if you have a package that wasn't part of the signature database that happens to map to indices that are all that all have a 1 stored in them, then the Bloom filter is going to say that signature is part of this database even though it isn't. And another thing to consider is that normal packages could potentially be used maliciously. So if there's a package that's sent during normal operations, it could potentially be injected into the network at a time when it's not supposed to and cause problems with the ICS. And so that's why it's important to consider temporal relationships between packages. So not only is a package part of that signature database, you also want to make sure that it's occurring in the network traffic at a time you would expect it to be occurring. And so that's where the time series level of the anomaly detection comes in. And so this is considering the temporal relationships between packages. So it's using previous packages to predict the next package as opposed to just considering packages on their own. And this is done using a stacked LSTM, which is a machine learning model that I'll touch on more in the next slide. And this is trained using non-anomalous data, that same training data set that is used for the package level. And looking more at the LSTM cell. So an LSTM is a variant of a recurrent neural network, and it was initially created to solve the vanishing gradient problem that's common in vanilla recurrent neural networks. And it does this by using gates to regulate the flow of data. So it has a forget gate at the front, which essentially decides what information from the previous cell state needs to be forgotten. And then there's an input gate, which determines how to update the cell state. And then there's an output gate, which determines the next hidden state of the LSTM cell. And so looking at how these are combined into the time series part of the intrusion detection framework, it starts with an input of time series packages. So not just an individual package, a sequence of packages in order. And it outputs a probability for all the signatures in our signature database. So say we have S signatures in our signature database, it's going to have a probability associated with each one of those signatures. And then the model takes the K most likely signatures and it compares the actual package to them. And if the package isn't part of those K most probable signatures, then that package is considered to be anomalous. So looking a little more in detail, we start with a series of packages which are discretized and then passed into the LSTM layers. And the output is a softmax layer, which essentially makes sure that the sum of the output probability is all summed to 1 across those S signatures. So then we end up with a set of S probabilities, and we take the K most likely signatures in that set, and then we compare the actual package signature to those K most likely signatures. And one problem with this is that you need to figure out the best way to determine the choice of K. And that value of K can have a big effect on performance. So if it's too low, then unless your model is really good, you're going to end up with packages that are being called anomalous more likely than not, and you're going to end up with a lot of false positives. And then conversely, packages, if you have that value of K set too high, packages are less likely to be called anomalous, and you're going to end up with a lot of false negatives. And so this is kind of a similar, choosing this value of K is pretty similar to choosing that discretization granularity from the package level. And they solve it using a similar, pretty much the same method. So taking that training data set, dividing off part of it as a validation set, and testing multiple values of K, and then choosing the lowest value of K that achieves a set acceptable false positive rate. And then there's another problem, which is that the model is going to be trained with non-anomalous data. So it's using a series of non-anomalous packages to predict what the next package will be. And so based on that, you can expect that if there is an anomaly in that set of previous packages, then the prediction is not going to be very good because it's never had to predict based on a series of packages that contains an anomaly. And so they solve this by adding probabilistic noise to data during training. And specifically, they add noise to packages with a probability based on how frequently those packages appear in the training data. And the rationale behind this is that packages that appear less frequently in the training data are more similar to anomalies themselves. So it's essentially emulating what would be seen during the real world application of this intrusion detection system. And so looking at how the package level and the time series level combine together, we start off with a package and take the signature of it, and that's passed in the Bloom filter. And assuming that it maps to all ones, it's considered normal. If not, it's considered an anomaly, and the process stops there since, like I mentioned, you can't have false negative lookups with a Bloom filter. And if it passes, then that gets passed on to the time series part of the anomaly detection. And so then it's considering the packages that came before it to determine whether or not that package is an anomaly. So now let's talk about the real world data set that was used to evaluate this framework. So this data set came from a SCADA system for a gas pipeline test bed. And the test bed consisted of an airtight pipeline, a compressor, and a solenoid controlled relief valve. And it was essentially doing a PID loop to control the air pressure in that pipeline. And communication with the SCADA system was done using Modbus. And here you can see these from before. These are all the features that are being communicated to the SCADA system as part of that Modbus payload. And they add anomalies or intrusions into this data by randomly injecting them with a script. And they use 7 specific types of attacks. So they inject random response packets, they hide the real state of the controlled process, they inject malicious state commands or parameter commands or function code commands, and they do denial of service, and they also do pretend reading from devices. So these are the 7 attacks that are being injected randomly into that real-world data set. So with that real-world data set, let's talk about choosing a discretization granularity. So there are 9 continuous features in that data set. So there's the time between packages, which is just the difference between the timestamps of those 2 packages. There's a CRC rate, and then there's a set point, pressure measurement, and then the 5 PID control parameters. And so looking at the time interval and the CRC rate, this is the distribution of those features across the training data. You see with these, there's pretty clearly 2 natural clusters. So that's just going to be an easy way to discretize these. So for each of these, we'll just have 2 clusters plus that 1 extra bonus cluster that I mentioned before for data that doesn't fit nicely into the 2 clusters. So yeah, you see both of these have clear bimodal distributions. And looking at the pressure measurement and set point, here there's not really any clear natural clusters. So with these, you're just going to discretize into even intervals. And then finally, with the PID parameters, which is a gain, reset rate, deadband, cycle time, and rate, these are all going to be highly correlated with each other. So they're going to be clustered together into a single part of the signature using k-means clustering. And so then with both the number of intervals for the pressure measurement and set point, as well as the number of clusters for the PID parameters, we need to determine values for each of those. So how coarsely or finely we're going to be discretizing those features. And again, we want to choose that to be as coarse as possible while still achieving a chosen false positive rate, which in this case is 0.03. So here you can see a plot of the validation error across different discretization values of the set point, pressure measurement, and PID parameters. And so from this, they ended up choosing to have the time interval and CRC rate split into those 2 natural clusters that we saw, plus the 2, 1 bonus cluster for each. And then the pressure measurement was split into 20 even partitions. And the set point was split into 10. And then the PID parameters were split into 32 different clusters. So let's talk about choosing a value of K for the time series level of the intrusion detection framework. So again, K is the number of most probable predicted packages that the actual package is going to be compared to. And if the actual package is not part of those K most probable predicted packages, it's considered to be an anomaly. So we choose that value of K by plotting the validation error for increasing values of K. And we want to choose a value of K that is as low as possible while still achieving a chosen false positive rate, an acceptable false positive rate, which in this case is 0.05. And since the training/validation data doesn't have any anomalies, any error is going to be classifying a normal package as anomalous. And so you can consider the y-axis of this plot to be the false positive rate. And so you see with a value of k equals 4, for everything except the training error with probabilistic noise, we achieve that 0.05 false positive rate. And so a value of k equals 4 is considered to be optimal by this parameter selection framework. Now, looking at the results of the framework on the test set, they still considered different values of k and how that affected the performance of the model. So this is a plot of precision versus k. And again, precision is the fraction of true positives over the sum of true positives and false positives. And you can think of it as being the fraction of flagged packages that actually were anomalous. And you can see here that adding probabilistic noise really helped the model, especially with low values of k. But you can also see that the model still generalized pretty well, even without adding noise, especially at higher values of k. But with higher values of k, there is a trade-off. So this is a plot of recall, and recall being the fraction of true positives over true positives plus false negatives. So you can think of this as being the fraction of anomalous packages that were actually flagged by the intrusion detection system. And you see here that the recall falls pretty quickly as k increases. And so this tells us that there were a lot of anomalous packages in the test set that were actually very close to normal packages. And so in order to pick up those, we had to introduce a higher false positive rate. And so now looking at the F1 score, and this is sort of a more rounded metric that considers the precision and recall trade-off. It's 2 times the product of precision and recall divided by the sum of precision and recall. And so we can see here that a value of k equals 4 achieved the highest F1 score with the probabilistic noise. And so that tells us that the method used for selecting that value of k did a good job, and it did choose the optimal value of k. And so now comparing with other models, there were 6 models that were used for comparison. So there's a Bloom filter, a Bayesian network, a support vector data description model, an isolation forest model, and then a Gaussian mixture model and a principal component analysis with singular value decomposition. And note that the first 4 models here are all supervised, and then the Gaussian mixture model and the PCA model are unsupervised models. And so looking at the performance of the proposed framework versus those existing models, we see that the accuracy of this framework was higher than all of the other ones, and it also performed better in the F1 score and recall. And the only models that really were able to compare to it were the Bloom filter and the Bayesian network. And that's because the other models really aren't designed to handle this complicated of data. And one thing to note is that the model didn't perform equally as well for each of the different types of attacks. So specifically for hiding the real state of the controlled process, as well as injecting malicious state commands and parameter commands, the model underperformed. And an explanation for this is that these attacks are closely tied to the physical process. And so it's likely that the model is interpreting these anomalies as just part of normal noise. So a solution for this would be to increase the amount of training data so that the model can learn what normal noise is versus anomalies. And also it would be helpful to increase the discretization granularity. And then the authors also proposed a method for dynamically adjusting the value of k to improve the performance on these certain attacks. So in conclusion, combining a Bloom filter with an LSTM is a very suitable framework for doing intrusion detection with an industrial control system network. And this is because it's able to learn from non-anomalous data. It's able to handle very complicated data. And with the methodologies laid out for choosing the parameters, namely the granularity of the discretization of the features for the packet level and the value of k for the time series level of the framework. Um, with those laid out methodologies using a validation set, it's actually pretty easy to train this framework. And with that, it does have a high detection rate. And in further studies, the paper laid out a number of things that could be looked into a little more, particularly using a dynamic value of k. And with that, that concludes my presentation on this paper. If anyone has any questions or comments, feel free to leave them in the pinned Piazza thread. Thank you.